Okay, so before we get started today, I wanted to make sure that you were all aware that I did put your test up over the weekend to put it up on Friday. I'll put the submission portal up later today. I'm happy to entertain any questions that you guys might have about it. I also use this weekend to edit the videos that have not yet been uploaded and all that kind of stuff. So they are edited and they are on my YouTube page, but I have not yet put the links on our course site. So I will do that this afternoon as well. All right. So today we are going to talk about the concept of magnetic actuation. So at the macro scale, magnetic actuation is something that we have all around us. It's the reason why electric motors rotate and all that kind of good stuff. It's also how magnetic storage media like hard disk platters and all that kind of stuff are read. So it's something that has been around for quite some time. At the micro scale, though, the applications have been limited. Can anybody think about why it might be harder to do magnetic related things at the micro scale?
Because the nearby objects will be affecting.
So that's not so much it. So what's the key part of most electric motors? The windings, absolutely right. So why do you think it would be hard to implement windings at the micro scale? It's hard to make anything that isn't a planar structure, right? And usually the coils that are associated with electromagnetic induction are solenoidal or toroidal, and that is going to be something that's pretty difficult to do for the most part if you're constrained to a single plane. There have been attempts to do it that have done interesting things. However, it takes a whole lot of effort and cost to realize those three-dimensional microstructures when the overwhelming majority of structures and processing are aligned towards two-dimensional flat planar things, right? So because of that, a lot of magnetic actuation at the micro scale relies on the use of permanent magnets, which have been deposited through electroplating and other processes. There are definitely coils that are still involved, but those coils are going to be planar coils, and so they're going to be extremely limited in the number of turns that they can have. And they also have a lot of flux leakage and things like that because of their structure. Okay. So before we can really get into the principles of magnetic actuation for MEMS, we need to have a brief review of magnetic field related quantities, right? So the first thing we're going to talk about is our H field, which I will refer to as the magnetic field intensity. And this is the driving magnetic influence external, and that is key, and that also doesn't look like good penmanship, to a material. So generally speaking, this is the magnetic field that we can control by choosing a particular permanent magnet or something like that, or passing a current through a coil. it is measured in amps per meter. And then we have our B field, which some people also call magnetic field, but I find that to be wildly confusing. Two different things called magnetic field. So I consider B as the magnetic flux density. And the distinction between our H and B fields is that our B field is the induced total magnetic field inside a material. It is measured in Tesla, where a Tesla is a Weber per meter squared. And since a Weber is nothing more than a volt second, we can have it as volt seconds per meter squared. Okay. So these two fields are related to each other by the susceptibility chi be an L and the permeability mu. Susceptibility is a unitless quantity. Permeability is really the combination of mu r and mu naught, where mu r is the relative permeability, and mu naught is the permeability of free space. Which is equal to 4 pi times 10 to the minus 7 henries per meter, where a henry is a volt second per ampere. So mathematically, our fields are related as follows. Our magnetic flux density, B, is equal to mu naught, the permeability of free space, times our H field, plus our M field, where this M field is the magnetization vector, okay, which represents internal magnetic polarization of a material that is subjected to an external field. So our magnetization vector M is, actually, let's expand this a little further. So we'll have mu naught times H plus chi H. So mu naught chi H is our magnetization vector. And we can further call this mu r mu naught times H, where we can see that mu r is 1 plus chi. So all of these things are related to each other. I personally prefer dealing with everything in terms of relative permeability, because I usually deal with electric fields in terms of relative permittivity. So it just makes the most sense to me to go that route. So different values of mu r mean different things. So for mu r, less than 1, and typically this is very slightly less than 1, we have diamagnetic materials. So what does diamagnetic materials mean? Well, it means that they, when they become magnetized, produce a magnetic dipole moment that is anti-parallel to the external magnetic field. So we see repulsion of magnetic forces when we have diamagnetic materials. This is how maglev trains and all that kind of good stuff work. You need a diamagnetic material like copper to be involved in your structure in order to get that repulsion and cause the train to effectively float on top of the track. For mu r is greater than 1, and again, we're talking about slightly greater than 1 here. We have paramagnetic materials. In a paramagnetic material, the magnetization vector will be parallel to the external field. So there's going to be attraction, an attractive magnetic force. But in a paramagnetic material, we're not able to establish any residual magnetism. So effectively, if you were to remove that external field, the attractive force goes away. And then we have materials where the relative permeability is much, much greater than 1. And by that, I mean usually thousands of times greater than 1. We have ferromagnetic materials. Usually made of iron and iron-related alloys. In a ferromagnetic material, we will observe that the magnetization vector tends to enhance the overall field. So we get very, very strong magnetization. Ferromagnetic materials typically have what we call domains, which are local areas that have their own magnetic dipole moments. In a general sense, these domains are randomly oriented, right? So let me just draw something silly here. Say we have a chunk of material, and I'm just going to break this down into lots of different regions. Like so. So our magnetic dipole moments will, generally speaking, be in random directions. And we should not observe any particular overall magnetic field strength in any particular direction. However, when we subject these ferromagnetic materials, to an external magnetic field, we'll find that the domains tend to align in the direction of the applied field. Now, this is true to a certain extent, but there's also something called shape and isotropy that we have to pay attention to as well. So shape and isotropy simply means that the fields are going to tend to align along the longitudinal direction of the medium. So if we were trying to magnetize a rod, the fields would align along the length of the rod. And we can observe this by wrapping a nail in a coil and then magnetizing it. We'll find that that nail will have a north pole and a south pole, and the fields will be, the internal magnetization will be aligned along the length of the nail, even if we were to skew the direction of the coil. We'll still find that the nail magnetizes along its length. Okay. Right.
The consequence of manufacturing the nail and how kind of the grain boundaries align in that process, or is that just a consequence of the fact that it's made out of concrete?
I think it's more, it's a consequence of the grain structure, I believe. It'll be easier to cause them to align along the longitudinal direction. I'd have to look more into it to give you a better answer to that. It's definitely related to the grain structures because that's what all of this is about. But I don't know.
Well, I'm just thinking if you're talking about the nails and rods, drawn out segments of metal.
Right.
Having to work it out into a shape, then cool it, heat it, cool it, heat it. You are moving the grain boundaries, but then you're also introducing sort of, what am I trying to say? As you're heating it and stretching it out, in addition to moving around the grain boundaries physically, you're also causing diffusion of materials.
Right, but so my question there, and this is let me be clear here that I don't know the answer to the heating process and all that kind of stuff. So when you heat a ferromagnetic material beyond its Curie temperature, it typically restructures the grain boundaries and reorients all the internal dipole moments and all that kind of stuff too. So I don't know what combination of effects leads to shape anisotropy, but experimentally it's been determined that typically speaking, the residual magnetization that we'll talk about in a moment usually winds up aligning along the longest dimension of the material. But I honestly do not know what combination of effects leads to that. So circling back around up here, we have this relationship valid for all materials, which looks like a simple linear relationship. However, in ferromagnetic materials, that is very much not the case. Instead, ferromagnetic materials tend to exhibit hysteresis. So I'm going to draw here a generic BH curve, also known as a magnetization curve. And we are going to see something like this, okay? So for small values of H, the B field will be, if I could draw a straight line here to save my life, roughly linear, right? But as our H field continues to increase, we'll have this knee region until we reach a saturation point, okay? So this section of the curve here, 1, corresponds to the initial magnetization of our material. There is an upper limit to the magnetic flux density strength that can be attained, which we're going to call B saturation. So effectively at this point, any further increase in B field, or excuse me, H field does not cause an increase in the B field, because effectively your field lines can only get parallel. You can't get any more parallel than parallel. As we remove our magnetic field intensity vector by just effectively turning down the current that we're using to generate the field, we'll see this region of our curve here too. So when our field gets back to zero, there is some B field in a net direction that's left over, right? So this is the residual or remnant magnetization of the material. So effectively, at this point, our material is behaving as if it were a permanent magnet, right? Because there is no driving or external field that's causing the B field to be in this direction. It is simply the B field that has been established in the material. If we continue in the negative H direction, meaning our current has changed direction, we will eventually get to a point where our B field is now zero. On the x-axis, this is going to correspond with negative HC, because we are effectively coercing, that's what the subscript C means. We are coercing our material to no longer have any residual magnetization. So we've applied a coercive field to completely demagnetize the object. And as we go even further in the negative direction, we will eventually saturate again. So this is negative B sat. If we were to then increase our applied field strength, until we hit H is equal to zero, we now have that remnant magnetization again, but it's negative. So effectively, our magnetization vector has completely switched directions. So if before we had a north pole on top and a south pole on bottom, now we have a south pole on top and a north pole on bottom for our permanent magnet. Continuing forward, we'll reach a point where our magnetic field strength, excuse me, our magnetic flux density is zero. So this is positive HC. So we've coerced it back to being demagnetized, and then increasing again come to here, and this cycles over and over and over again as we effectively change the direction of the applied current that's generating our field, right? One thing, and I just learned about this actually very recently, and by that I mean this weekend, is the concept of magnetostriction. Okay. So effectively, if we don't ever drive our device into, or drive our magnetic field into saturation, drive the magnetic flux density of our material into saturation, we're in a magnetostrictive region. And some materials in this magnetostrictive region experience a stress due to an applied magnetic field. So it's similar to piezoelectricity, except that it's a magnetic field that's doing it. Now, what's interesting is that this stress can cause the material to elongate or mechanically deform. And so there are things called magnetostrictive drives, which effectively you wrap a coil around a material and then you just pulse current through the coil, and it causes the material to slightly expand, contract, slightly expand, contract, slightly expand, contract. and you get this inchworm-like movement or actuation of the material inside the coil. Okay. I haven't been able to find anything about that being used in MEMS devices, but I thought it was very interesting and I learned something new. So I figured I'd tell you guys about it. It's a pretty neat actuation scheme. So anyway. So let's see. So we have our initial magnetization. Then we have residual magnetization. Section 3 is coercion. And then 4 is magnetization. In the opposite direction. So I say most, but to my knowledge, all ferromagnetic materials, we have this nonlinear relationship between our H field and our B field that is governed by this hysteresis curve. Now, the area of the hysteresis curve effectively represents the amount of energy it takes to magnetize and then change the direction of magnetization of the material. So different materials are going to have slightly different hysteresis curves. They're all going to generally look like this, but they're either going to be wide-waisted or narrow-waisted, right? So effectively, the coercive field is either going to be large for a wide-waisted material or small for a narrow-waisted material. So if the width of the hysteresis curve is large, we have hard, no, good God, no. Magnetic materials, okay? So all this means is that it takes a lot of energy to demagnetize this object. Where might this be useful? Magnetic media, right? So storage media. We don't want to be able to easily erase the data. We want to have to intentionally apply a field to change the state of that bit from a 0 to a 1 or vice versa, right? If the width of the hysteresis curve is narrow, we have what are called soft magnetic materials. Soft magnetic materials are what are used in transformers and induction motors, because we know we are going to have these things hooked up to the sinusoidally varying current. And so we want the magnetization to switch back and forth very easily so that we don't incur a lot of losses in that electromechanical transduction. Right. All right, so I think we have a basic understanding of the relationship between our B field and our H field. Now let's go a little bit further and talk about the Lorentz force law. Okay. So the Lorentz force law is probably the most commonly used magnetic actuation scheme, okay? The Lorentz force law is why induction motors turn, right? Or why the rotors turn. And it simply states that force F is equal to QV crossed into our B field when we're dealing with point charges. And it is IL crossed into B when we're dealing with current carrying conductors, where the L vector is really just telling us the length of the conductor and also the direction in which our current is flowing. Okay. So let's look at a microstructure that utilizes the Lorentz force law for actuation. So we have permanent magnet over here on the left. Permanent magnet over here on the right. Such that our B field is oriented from right to left. Okay. Between these permanent magnets, we have a plate. Like so, where this guy right here is a torsional hinge. Oh my goodness, I cannot write. Same thing on the top. Okay. So the top of this plate is polished because it's going to serve as a mirror. Okay. So effectively, we have a mirror attached to a torsional hinge. So it's a scanning mirror, and it's going to reflect depending on what our torque that we were able to induce in this thing is doing. On the back of the plate is a planar coil. And that curved bit there represents effectively that we have to have somewhat of a 3D structure that is going to allow the return path of our current to go up and over our coil. And let's say, for the sake of argument, that our current I is flowing into the coil in this direction, right? So if we were to look at this thing, what we would see is 1, 2, 3. So if I'm looking at this system along this cut, and I've rotated it up 90 degrees so that I'm looking down the barrel of the coil effectively. Let's say that our current is oriented out of the board for the 4 right conductors and into the board for the 4 left conductors. our B field is oriented in the plane of our plate, like so. And we are going to see that each of these conductors is going to experience a force based on that F is equal to IL crossed into B. So if the direction of our current is coming out of the page and our B field, I'm trying to think how to do this, is going from right to left, our conductors on the right-hand side are going to experience a force in the down direction, right? So our index finger is the direction of the first term in our cross product. Our middle finger is the direction of the second term in our cross product, and our thumb is the direction of the resultant force. That's how the right-hand rule works. We're going to see that all four of these right-hand wires experience force down. And all four of these left-hand conductors experience a force up. What's that going to do to the plate? Going to rotate it, exactly right. So it's going to cause a torque. Like so, because we effectively have force pushing down on this edge and a force acting up on this edge. So it's going to cause the plate to twist. If we were to reverse the direction of the current, our torque will be in the opposite direction. So we can cause it to scan from left to right and from right to left, depending on the direction of the current that we apply. The magnitude of the torque is going to be I, B, L1, L2, N, where I need to define what L1 and L2 are. So L1 is the average length of the conductors in direction parallel to the edge of the permanent magnet. Right. Secondly, all of our conductors aren't of the same length because we have this planar coil. So the outside run is longer, then it's slightly less for the next one over, slightly less, and so forth and so forth. So we're going to have some average conductor length. And then L2 is the average distance between the wires in the direction perpendicular to the torsional hinge. Axis, and N is the number of turns of the coil. So we can figure out what our induced torque is. And then knowing our plate dimensions, we can determine the amount of displacement we see of the plate and all that kind of good stuff. And we can also compare this induced torque to the restorative spring torque of our rotational springs as well. If I were to, I don't know, assign you a problem asking you to do something like that. which seems quite likely. All right, so this is a simple single axis scanning micromirror. Okay. Now let's talk about simple magnetic force, attractive and repulsive forces here real quick, right? So we know that from the experiments we all did as little kids and stuff like that, that when we have two permanent magnets, if you try to get two north poles close to each other, there's a considerable amount of push. Whereas if you put a north pole close to a south pole, they attract each other very easily, right? So that principle has also been used in MEMS magnetic actuation. Okay. So let's look at another structure here. It's going to be pretty similar to the one we just looked at. So we have a gimbal in this case, just a rotating frame. So this structure is our gimbal. And then on the interior of this gimbal support structure, we have a plate. So this is a torsional spring, as is the one on the left-hand side. This is a torsional spring, as is the one on top. So in this configuration, we have 2 degrees of freedom instead of 1. So we have rotation in 2 different directions, right? So let's say that our B field is oriented out of the face of our plate in this case, right? So vastly different direction than we saw last time. And along our axes, I guess, symmetry here, we can divide our plate up into 4 quadrants. And on each of these quadrants, we can pattern a planar coil. All right. So we have a mirror suspended on a 2-axis rotational gimbal. We have 4 quadrant planar coils that are patterned on the back side of our mirror plate. And as each of these coils carries a current, it will have an associated magnetic dipole moment that will depend on the direction of the current passing through the coil, right? So let's say, for instance, that our top left coil, the current is flowing in a counterclockwise direction so that the magnetic field is oriented out. The same thing for this guy. And then the 2 right-hand coils are carrying a current in a clockwise direction so that the magnetic field is oriented in. We are going to see that a torque is produced that causes rotation in that direction, right? So our torsional hinge on the top and the bottom is going to experience a rotation. If instead our two top coils generated fields out of the page and our two bottom coils generated fields into the page, we'd see that the bottom part of our plate was being repulsed by our external magnetic field. And so we would have a torque in this direction. And there are four different states that we can put our different coils in to cause torques in four different directions. Okay, so we have scanning like this and scanning like this. So we have a two-axis scanner that uses the repulsive and attractive magnetic forces for its actuation, right? All working on whether or not the dipole moments are parallel with the field or anti-parallel with the external field, right? So this type of device literally has a permanent magnet affixed to the back of the substrate so that the entire mirror structure has a field all in one direction. The last one we're going to look at is a switch. So let's say that we have a cantilever switch. That is connected to a torsional support structure. Like so. So here's our anchor, torsional support. And then this is going to be a permalloy cantilever, where permalloy is a soft magnetic material. And let's say that over here, we have a coil, okay? So this is our top view. Our side view is going to look something like this, okay? So this is our permalloy cantilever. But on the bottom, it's been gold plated. Gold plated specifically to make good electrical contact with contact down here. And this contact sits on top of a substrate. Way over here on the left-hand side, we have our coil. And then on the back of the substrate, we once again have a permanent magnet, okay? So this is an example of really two things we haven't talked about yet. Bimorphs, so that's just a structure made of two different materials. So this would be a bimorph cantilever made of permalloy and gold. And then it's also bistable, meaning that it will be stable in an on position and stable in an off position. And then the switching thing is point of instability, okay? So the bistability of this switch means that it's 2 points that it wants to be in. It's 2 operational points. So here's our external H field. Are going to look something like this. So this is the point in the middle. In this case, our magnetic field, excuse me, our magnetization vector is like so. And we are in an off state because our gold layer has been lifted up from the surface of the contact. And then in the opposite, we have something like this. Where our gold layer will be in contact with our contact. Here's the direction of our magnetization. And this is the on state for the switch, right? So let's talk about how this device operates, okay? So we have a permalloy cantilever. Permalloy specifically because it is a ferromagnetic material that is soft, meaning it is relatively easy to change the direction of the magnetization vector, right? So it is a ferromagnetic material, which means it contains or is capable of having a residual magnetization. And because it's soft, it's easy to change the direction of this residual magnetization. The residual magnetization will in general be along the longitudinal axis of the cantilever. So the cantilever is much longer than it is wide or that it is thick in order to sustain this. And so effectively, in one particular magnetization direction, the permanent magnet will attract the cantilever beam and it'll be closed. Okay. In the other direction, it'll be open. And it's got a hybrid drive system effectively. So it uses not only the permanent magnet, but also the coil. So effectively the coil is what's used to reverse the magnetization vector of the cantilever, causing it to go from one state to the other. And what's very interesting about this is it's bistable, meaning it has latching, okay? So it's the attraction between the permanent magnet and the magnetization of the cantilever itself that's causing it to stay closed so that it doesn't require power to keep the switch closed. When we talk about electrostatic switching, when we get into talking about RF MEMS, one of the biggest problems with that is that the switch only stays closed when you're supplying power to keep it closed, right?
So you only need power if you want to change the state.
Exactly right. So that's the biggest use of this is you have the contact is maintained or the switch is closed or the switch is opened. It's holding the switch holding the switch closed or holding the switch open does not require external power. Only changing the state of the switch does. Whereas when we talk about electrostatic switching, we'll find that it requires a particular voltage to cause actuation and then a smaller voltage to maintain the state, but it's always consuming DC power. The issue with this is that it's not CMOS compatible by any stretch of the imagination because it requires electroplating and the application of permanent magnets and all that kind of good stuff as well. So, all right, so that is enough out of me for today. Yes.
So quick follow, if we're using this as a switch that you can change states for the applied voltage,
Mhm.
putting energy into it. How does the performance of this compare to using transistors for switching instead? Because those require constant power.
Right. So these are used for higher current density applications, right? So particularly if we're considering integrated MOSFETs as our switches versus these, the current density that these can handle without undergoing, trying to remember what the right word is.
Burn saturation.
The tendency of passing too much current to literally cause the wires to melt and move, which we talked about in our integrated circuits class, but now that the name of the phenomenon is escaping me. Sorry, what?
Ohmic heating.
No, I mean, that's got something to do with it, but it's, electromigration. There we go. Yeah, so with small wires and all that kind of stuff, small traces like we would typically see in a transistor, we have a large opportunity for electromigration if the current that's being passed is large, because we're effectively have a small area that we're passing a large current through, and it can deform because of that. For this, we have much larger contact areas and all that kind of stuff, so we can handle a lot more current. And then also, we don't have to worry too much about electromigration. One thing that you do have to watch out for, though, and we'll talk about this when we get into electrostatic switching, effectively, if you use gold, which is an easily deformable contact material, right? So you can literally stretch it and all that kind of good stuff. It's very, very ductile. Well, repeated switching applications is going to cause mechanical deformation of your contact and your switch structure, right? So you do have, there's a limited lifetime of the number of switch cycles that you can do with a mechanical switch like this that you won't see in an electrical switch like a transistor, because there's not actual material making contact constantly hitting each other.
And if you're switching states, in addition to mechanical deformation, you're talking about high voltage potential, could we potentially pull apart as you're closing distance?
So you could, that's called stiction, you could deal with as well. So that would be effectively like welding the two, the contacts closed. That is also a possibility. That's going to be true any type of mechanical switching you have at the MEMS scale. There's always the potential for stiction as well. So the electrical contact gets made and it welds the two materials together. Some is beyond what we're talking about right now. So some capacitive switching, electrostatic switching things actually use a thin insulating material over one of the electrodes. And so it's not so much that electrical contact is made, it's that there are two different capacitances, because you would see the air gap in series with the insulating material or just the insulating material, and that change in capacitance is enough to drive the switching operation. So we'll talk about that probably in a week or so. Anything else? Alrighty, well, we'll see you guys on Wednesday for what I'm going to call thermal actuation for right now, and we'll see what happens.